Okay, so during our last lecture of Friday, we start seeing some of the parameterization that we will use in order to describe the attitude of a 3D body, of a 3D rigid body in the 3D Euclidean space. So far, we have seen two methods, two ways that we can adopt to describe such rotation: Euler's parameters and Euler's angles. We have seen that both of these two techniques have pros and cons. In particular, we have seen that, for example, Euler's parameters have the disadvantage of being 4, needing an additional constraint equation to close the parameterization, leading to the final number of 3 parameters, linearly independent parameters, which we need to, let's say, describe the orientation. But on the other hand, we have the advantage of having no problems in terms of singularities, okay? Then we have also seen the use of Euler's angles. In this case, we have 3 parameters, so no need to an additional equation to close the formulation. But we have other disadvantages, the main being the so-called gimbal lock, okay? Meaning a condition in which we have that 2 of the 3 axes of rotation that we make use of in order to describe the orientation of our body become collinear. And in practice, we are not able anymore to describe the full spectrum of the orientation possible for the 3D body. Okay? Of course, we have specialized this kind of study for the single body, but of course, we will see that this can be replicated, of course, for a system of various bodies. Okay? So today, the idea is to go through another technique that we can use, which is kind of popular in the field of multibody structures, which is Rodriguez parameters, yeah? The one represented by Rodriguez parameters. And then eventually we will start seeing some of the properties, the mathematical properties that are possessed by a rotation matrix. Okay, so after seeing how we can actually describe and parameterize the orientation, we will see what are, in fact, the mathematical properties of the transformation matrix. So, without further ado, we will start seeing this other technique, which is, as I said, called Rodriguez parameters. Okay. So again, we have 3 parameters. All right. We will see what these 3 parameters are. So remembering that our transformation matrix was obtained as the identity matrix plus the skew matrix mi tilde times the sinus of theta, where theta is the rotation angle squared okay? This is Rodriguez formula. So, well, we define, just a second, because this is just too much. Ragazzi, noi stiamo facendo lezione, vi chiedo di fare meno confusione. Okay. So, we were saying, we define the vector gamma as the vector ni, which is the unit vector indicating the axis of the rotation that we want to describe, times the tangent of the angle theta divided by 2. So that eventually our three components of this vector, gamma 1, gamma 2, and gamma 3, can be defined as μ1 tangent of theta divided by 2, μ2 theta divided by 2, and n tangent of theta divided by 2. Okay? You should be able now to see right away what is the disadvantage of this technique. You have singularities, okay? When the argument of the tangent becomes pi divided by 2. So when theta is plus minus pi. Okay? All right. So this is the real disadvantage of this formulation, which is typical for all formulations that use three parameters, as in this case, typically that's the drawback. Okay, let's try now to express. So this is by definition. Again, let's see how to make use of this in order to be able to express our transformation matrix. Okay? Okay, so let's see how to express our rotation matrix in terms of these parameters. So first of all, we have that. So now we're going to have just some algebraic manipulation so that we can make use of the of these parameters to be able to express our transformation matrix. So sinus of theta is, as we know by the bisection formula, is the 2 times the sinus of theta divided by 2 times the cosinus of theta divided by 2. And this, in turn, if we divide and multiply times cosinus, we have 2 times the tangent of theta divided by 2. If I divide this by cosinus, and then I multiply by cosinus, times cosinus squared of theta divided by 2. Okay? I divided and multiplied times cosinus. Then, of course, I can write that this is equal to what? 2 times the tangent of theta divided by 2 divided by 1 divided by cosinus of theta squared divided by 2. Okay? I think this is apparent, no? So 1 over the cosinus squared is the secant. You know it, right? So we have that 2 tangent of theta divided by 2 divided by the secant squared of theta divided by 2. Okay, so 1 over the cosinus is the secant by definition. Okay, all right. And the secant, always by trigonometric formula, is 1 plus the tangent square of theta divided by 2. Okay? So this is this. These are always trigonometric properties that I make use of. Okay, so this is the first noteworthy result that we wanted. So now we have that gamma transposed, as we have defined it before, applied over gamma, that's to say the scalar product of gamma on itself, is equal to what? If you want, I can write it down. By definition, it's mi transposed, apply over mi, the square of the tangent divided by theta 2. All right? So this is 1 because these are unit vectors. Okay? So this is the tangent squared of theta divided by 2. And this, by definition, we define it as gamma squared. Okay? We call it gamma squared. So if we put everything together here in this board, we can write what? That the sinus of theta is equal to what? To 2 times the tangent of theta divided by 2 divided by 1 plus gamma squared. Okay? So I highlighted it in red. Okay? This is the first, let's say, result that we needed. Okay? Okay. Now we have a second result that we need. So good? Okay. So the second result that we need is the following. So the sinus of theta divided by 2 is equal to what? Always by definition. We have seen it before, so we have that. So out of curiosity, sinus of theta is equal to 2 times the what? The sinus of theta divided by 2 times the cosinus of theta divided by 2. So this is the bisection formula that we used before. So the sinus of theta divided by 2 is what? Sinus divided 2 times cosinus. All right, so let's write it. So it's sinus divided 2 times cosinus of theta divided by 2. All right. Okay, but the sinus we have just derived before. So let's substitute it. It's 2 times the tangent of theta divided by 2 divided plus 1 plus gamma squared, and this is the sinus, times 1 over 2 times the cosinus of theta divided by 2. Okay? So this is, allow me to cancel all this. So let's just simplify the 2, and let's get here. So it means that the sinus squared of theta divided by 2, what is it? It's this thing here multiplied by the sinus of theta divided by 2. Okay? If this is this, if I want the sinus squared of theta divided by 2, I multiply this by the same. Okay? So let's do it. So it's the tangent of theta divided by 2 here, divided by 1 plus gamma squared, plus the cosinus of theta divided by 2. Okay? I just rewrote the sinus of theta divided by 2. Now I have to multiply it. Okay? So the sinus of theta divided by 2. I don't think it's difficult at all, no? Okay, but this is what? The tangent. Okay, so let's do it. So this is the tangent squared of theta divided by 2 plus 1 plus gamma squared. Now, if you have seen it, we have derived the two parts which are in the Rodriguez formula, the sinus of theta and the sinus squared of theta divided by 2. Okay, so let's substitute it in A. So substituting in A, what do we have? That A is equal to what? 2. The identity matrix which stays there, plus 2 times 1 plus gamma squared that multiplies ni tilde tangent of theta divided by 2. This, if you see, is the sinus of theta. We have seen it before. Plus ni tilde square times the tangent of theta divided by 2. Okay? So if you want, let's use all the proper brackets. So we can do it like this, we can do it like this, and like this. Okay? Oh, sorry, here it's squared. It's this one. Okay? Now, just to make things more easy, we define this. We define this as gamma tilde. Gamma tilde. All right. So let's write it, in fact. So we define our gamma tilde as our ni tilde times the tangent of theta divided by 2. Okay? Therefore, our ni gamma tilde is always the skew matrix 0 minus gamma 3, gamma 2, gamma 3, 0, minus gamma 1, minus gamma 2, gamma 1, 0. You see, it's always an antisymmetric matrix. With, you can write it, gamma, the vector is equal to gamma 1, gamma 2, and gamma 3, as usual. Okay. In any case, with this definition, we have eventually that our transformation matrix becomes the identity matrix plus 2 times 1 plus gamma squared over gamma tilde plus gamma tilde squared. Okay? So you see, if you have, what's the point of all this? You have theta, so you have the axis of rotation and the angle of rotation as usual. You define the gamma vector to basically define all the Rodriguez parameters. Then from this vector, you get the skew matrix, easily like here. And using this formula, you get your transformation matrix. Okay? So very easy. Now, let's see how we can pass from Rodriguez parameters to Euler's parameters. Okay? Okay, so because you can have sometimes the need to do so. Okay, from Rodriguez to Euler's parameters. So, ni I, which is the height component of the vector of Rodriguez parameters, so ni 1, ni 2, or ni 3, gamma 1, gamma 2, or gamma 3, sorry, is by definition, because we have defined it, ni I times the tangent of theta divided by 2. Okay? Oops. By definition. Then again, let's split the tangent into 2. Sinus of theta divided by 2 and cosinus of theta divided by 2. Now, did you recognize this? This is theta I, okay? The parameter, and cosinus of theta divided by 2 is theta 0, okay? Okay, so just to be clear, this here is this, and this here is this, okay? So you pass from Rodriguez to Euler. Now let's see how we do the way back, and then we're done. So you see nothing really complicated here. All right. So here we said, yeah, from Rodriguez to Euler. Then is from Euler to Rodriguez. Parameter. Okay, so we have that the cosinus squared of theta divided by 2, and then a square root of it, is equal to the square root of 1 over 1 plus gamma squared. Why is it so? Because this means that the cosinus of theta divided by 2 squared is equal to the argument of this square matrix. But we have already defined it, demonstrated this. Why? Where? So let me show you. We have just done it. Did you see here? Here, we have basically that if you, from here, where is it? Where is it? There you go. Okay. So this is the sinus, and this is the cosinus of theta divided by 2. So if you do it the square of this, from here as well, you get, so here and here, the cosinus squared of theta is 1 over 1 plus gamma squared, okay, from here. So if you want, I can use this, and then write, if you, to help you out remembering, from there. But what is this? This is exactly theta 0. Equal 1 over the square root of 1 plus gamma squared. But then again, from, if you want, this triangle here, which is this, You see? You have that basically theta I is basically theta 0 times theta I is equal gamma I times theta 0. No? Then let's do it here. From we have that theta I is equal to gamma I theta 0. And therefore, theta I is equal to gamma I divided by 1 plus gamma squared. Okay? And this is it. Okay.
Questo è da Rodriguez
Yes, correct. Yeah, that's correct. So let's switch it. True. So this basically closes the explanation over Rodriguez parameters. Very easy. All right, now I wanted to present you some properties of the transformation matrix. Okay? And in particular, I think we will only have time to demonstrate the orthogonality of the transformation matrix. Who knows what the orthogonality of a square matrix means? So, let's say mathematical properties of A. So that's our topic. And let's start with the orthogonality. Orthogonality. When does a matrix is orthogonal to itself, of course? Correct. So we have to demonstrate that this is equal to this. And we will see that there are two ways of demonstrating it. One, which is, let's say, more, let's say, formally sound, and the other one, which is more intuitive. All right, so demonstration. But then we first observe one thing. We observe that you can do it if you want. The power of 3 of the ni tilde, so the ni tilde applied 3 times over it, sorry, ni tilde, I keep on switching and that's not very clear, but ni tilde applied 3 times over itself is equal to, as we said, ni tilde applied over ni tilde over ni tilde. And this is equal, I invite you to demonstrate it, to verify it, to minus tilde. okay? Because it's a square antisymmetric matrix. By the same reasoning, you can demonstrate that ni to the fourth tilde is minus tilde to the second. Okay? And for example, if you want to notice, is that to the fifth, so if you get up by order of the power, this is equal to ni tilde. Okay? In general, the relationship is the following. In general, the following holds. That ni tilde to the end. Actually, let's write it first with this 2n minus 1, where n is a natural number. So this is an odd number. Okay? Is equal to minus 1 to the n minus 1 applied over ni tilde. Okay? So with n belonging to n0, so which is this is the ensemble of the natural numbers without the 0. Okay? And here we have 2 times n is equal to, again, minus 1 to the n minus 1 ni squared. So it means that you can always, the odd power of ni tilde can always be traced back to ni tilde with positive or negative side depending on the order of the power. And when you are dealing with even powers, you can always track it back to ni squared plus a proper coefficient. Okay, let's denote these two results like this, okay, with this sign, because then we will make use of it. All right. Let's now see what is the product. Let's calculate the product of A transpose applied over A. Okay, let's just at first write it again. So this is I. Now, I should write plus ni tilde transposed, right? But what is the transpose of a skew matrix or an antisymmetric matrix? It's the same matrix with a minus in front of it, right? So I can put this and replace it with a minus. Okay. Times of theta. Then I should do the same stuff with a square. All right, but then I would have two minuses. Okay, I should write plus ni transposed and ni transposed. Okay, they both would give us a minus sign, so eventually we would have a plus sign. So I rewrite it as this. This stays the same basically. Okay. And then the sinus of theta divided by 2. So this is the first part. And then the second part, which is the usual one. So I okay. All right, now let's make the product, but let's make it in a smart way if you want. Okay, I times I is I. An issue?
Professor, there is a hint that divided by 2 in the second in the first scene.
Yeah. No, because this, sorry, here this is the mistake. This is the sinus of theta. Huh? Okay, that's the mistake. So I times I, it's always the identity matrix. And so far, so good. Now, yeah? See? Thanks. Correct. So now, what would we have now? So we would have I times this and I times this, okay? And then we would have this times this, okay? So it means that this multiplied by this and this multiplied by this would cancel out. It means that we have no power of 1 of the sinus, okay? Again, this times this and this times this would cancel out, okay? Then let's see about power of 2. We have this times this, and then we have this times this. Okay, so let's write it. Plus 4 e tilde squared of the sinus of theta divided by 2 squared. Okay. Then what else do we have? We have always in terms of the square power, we have this times this. Okay. Sinus of square of theta minus, so we have minus square of the sinus square of theta. Okay. It's this times this. Okay. Correct? All right, and this is everything for the power of 2 of the sinus. Now, if we go and check the power of 3, the third power, we would have this times this, but then again this times this. Okay? And they will cancel out again. Okay? So we are only left with the power of 4th, which is this times this. Okay, so let's write it. Plus 4 times e to the 4th sinus to the 4th of theta divided by 2. Okay? And this is all. Now, if you consider what we have just written, if you remember, look at this. What I want to do is to basically rewrite our equation, making use of this. So bringing everything up to the power of the 4th on e. Okay? So if you want, I can do this. Let's make use of this. And let's rewrite. So if we make use of star, the green star, we can write the following, that A transpose apply over A becomes, so I stays there. Then let's see from here. So this becomes what? Minus 4 times the ni tilde square to the fourth of sinus squared. Okay, that's it. All right. So let's write it. Minus 4 times to the fourth of sinus squared of theta divided by 2. And the rest, well, we do also it here. And this becomes plus ni to the fourth here. Okay, so let's write it. Plus 4 sinus of square of theta, and the rest stays the same. So plus time, 4 times. Okay, we're almost there. Okay. Okay, so let's rewrite it. Here we rewrite sinus squared of theta divided by 2 plus, now this, we have to rewrite it again using the bisection formula that we have just seen, so that everything becomes the same. So this is 4 times the sinus squared of theta divided by 2 cosinus squared of theta divided by 2. So let me just highlight it. Okay, this is this part. So you see that now everything is coming back together, plus this, 4 times to the fourth. Now, what I can do, and then I'm done basically, is putting in evidence 4 times ni to the fourth of the sinus of theta divided by 2 squared. Highlighting what? Well, I have basically, here I have what? The sinus squared of theta divided by 2. Okay? From here. From here, I get the cosinus. And from here, I get minus 1. Okay? What's the value of the quantity between square brackets? 0. Okay, so this is the null matrix, in fact. And this proves what? And so it follows that A transposed applied over A is equal to the null matrix, and therefore that the transpose is equal to A to the minus 1. Okay? Okay? Clear? Huh? Huh? Ah, sorry, yeah. This is new and this is identity matrix. Yeah, sure. Okay. There you go. Okay. Okay. So next time, we will see that there is another way to demonstrate it in only a couple of passages. Really. More intuitive, less formally correct, but still important. Why is it important to know this? Because we can basically say what? That when we will be able to assign also, apart from actually exploiting this mathematical property, we will be able to assign a physical, if you want, meaning to this. What's the meaning of this? That basically, when you are applying to a vector the inverse of the matrix, you are basically considering a counter rotation. So if A is the matrix that if you apply to a vector, rotates the vector of an angle theta, if you apply A to the -1, you are rotating of the angle minus theta. So you are rotating it back where it was before the rotation. Okay? We will see this, let's say when is it? Next time. And that's quite useful from a mathematical standpoint, but also to understand what's the, let's say, value intuitively of this operation. And this is all.